All right, good afternoon, everyone. If you have not yet had a chance to read the announcement, I posted an announcement earlier today. Homework assignments are posted on Canvas, homeworks 1, 2, and 3. Typically, I like to post anywhere between 3 and 6. And then, of course, depending on how fast we cover the material, I could either delay them or not. So the first homework assignment is due the Sunday after next. So you have 9 or 10 days to get that one done. And then second is the Sunday after that one, and the third is the Sunday after that one. So then every single Sunday after that one. So 3 Sundays, and then maybe if the material is not covered, then I might postpone it by a few days. But as of now, they are due for the next 3 Sundays after next. Okay. You can find them under assignments tab, and there's a PDF on there. You download the PDF. It has the questions and the points. This homework, my philosophy about homework is that homework is practice. The homework is part of your learning. So if you don't know stuff, you shouldn't be losing. Students shouldn't be losing any points. Okay. So you do the homework as best as you can. Come see me if you have any questions. You can work in groups. That is fine with me. You can use an AI tool if you want. That is also fine. Just be aware that AI tools can become a crutch. So if you've been using it for a while, you should endeavor to be more than the AI tool, meaning you should know more than what the AI agent does. Okay. So if you want, you can use, refer it to for help and assistance, but ensure that you're understanding what you're doing. Okay. So do the best you can on the homework, and then, we'll grade them, and then we'll see if you're going to lose too many points on it. I'll allow a second submission so that you can recover those points back. Okay. So again, while you're in the process of learning, I don't want students to lose points because they don't know some things, right? The other announcement was about the lecture videos. The lecture videos have been posted after every single class, but I overlooked linking the playlist to the Canvas page. So I did that earlier this week. So it was linked on, I think Tuesday or sometime I already linked it. So let's see. I just want to share that. From the front page, sorry. This is the front page of Canvas. And then you click on, that's 201. Come on. 115. So lecture videos, you click on that. It takes you to this place, winter of 2026, section 01. It's right here. This links it directly over there. I would like to point out this channel, or that entire account of the channel that I have on YouTube is not monetized. Okay. So increasing the subscriber count, I don't really care about that. If you want to subscribe, that's fine. It's not going to make me any money. The more people who watch it, I'm not making even a single cent on it. I just kept it free and open for anybody in the world who may find it useful. Okay. Especially, of course, it should be beneficial for students in this class. If you have the occasional absence, or if you want to review the material and go back, you can refer to these videos. Okay. And then, of course, the quiz schedule is already on there. Make sure you're aware of everything that's on the website. Okay, let's go to our notebook. Where is my, okay, there it is. And we had stopped here, so we were kind of a rush at the end, and I'm going to take my time going over these concepts today. Let's see. Okay. The previous slide, we had talked about connecting meters to take some measurements, specifically the ammeter and the voltmeter, right? You already had a lab, right, in 145. Have you all learned how to use a multimeter in the lab, right? So again, so it's so-called multimeter because it can measure multiple functions. It can measure voltage, current, resistance, capacitance, diodes, etc., etc. So multifunction meter, and it's digital, so it's DMMs. Now, olden times when they were first invented, we had analog meters and they were specific purpose. So an ammeter would only measure amps, voltmeter would only measure voltage. Now, You have these digital meters with like front panels, fancy programs, fancy controllers. So every time you wish to measure a specific quantity, we have to change the mode of operation. So if you wish to measure voltage, there should be a button on there. Doesn't matter what manufacturer or what model it is. Sorry, which manufacturer or what model it might be. There should be a button on the front panel that allows you to put into voltage measurement mode. Now, when you put it into voltage measurement mode, between the terminals of the meter, you would see infinite resistance. Ideal voltmeters have infinite resistance. Real life voltmeters will have very, very high resistance. And then when you put it into current measurement mode, some meters will say A, some meters might say I. A for amps or I for current. So as engineers, you should be comfortable working with a variety of instruments. Now, when you switch it to current measurement mode, ideal ammeter or current measurements would have 0 ohm resistance, right? And that's what these statements mean. So let me explain. Let's say we are trying to measure the voltage across this resistance, right? Doesn't really matter what that resistance is or what the voltage is. But now let's say this, right now we are using 1.44 amps, 1.44 ohms, which is very small resistance. Instead of 1.44, let's say we use something like a 1 kilo ohm resistance. Okay. And then you connect a meter to measure that voltage across the 1 kilo ohm resistance. Actually. So what happens? If this meter also has some resistance, actually not also, it does have some resistance. So when you connect a meter, we can model the meter as having some internal resistance. Let's call it R internal of voltmeter. Okay, of voltmeter. And when you connect it in parallel, if there is current coming from here and going through that resistor, which is causing a voltage drop, if you now connect another resistor in parallel, you have now provided a second pathway for that current to flow through. Does that make sense? Without knowing anything about series or parallel connections, if you see a current coming this way, there's only one pathway to go. So it's going to that 1 kilo ohm resistor. But now if you attach a second resistor in parallel, now there is a second pathway for the current to flow through. So some of it goes down 1 kilo ohm, some of the other current might go down the meter itself. Make sense? Right? If it goes through the meter, it's going to cause a voltage drop. And for that reason, we want that resistance to be as high as possible. Ideally, we would want it to be infinite. Ideally, we'd want it to be infinite so that no current passes through it. And if no current passes through it, that means everything goes to the 1 kilo ohm resistance and you're actually measuring the actual voltage. Okay. And that's the point of saying it will not divert any current. That means R should be equal to infinity or infinite ohms. Let's take a pause. Think over that. Let me know if you have any questions. Does that make sense? Okay. So similarly, if you have current measurement, well, in order to measure current, Oh, one more thing about voltmeter. So when you're taking voltage measurements, voltage is measured between 2 points. So we do not need to break any connections in the circuit. We simply take the 2 leads of our meter and we just connect it across those 2 points. So voltage is always measured across a component or across between 2 points. Current, however, so to measure current, the current must pass into the meter. So it must go through the meter. If it needs to do that, that means we need to break the circuit. We need to break a connection in the circuit where we want to measure the current. So the meter is actually inserted. In order to measure current, we always must disconnect that branch of the circuit, insert the meter in the middle of the pathway so the current goes through the meter, and then we can take the measurement. So voltage measurements are very easy. You can measure voltage on a live circuit, meaning the power supply is on. You simply connect your meter and you can measure the voltage. For current, you need to turn off the power supply, disconnect the branch, insert the meter in the middle, and then turn on the power supply again. Okay, that's something you should practice when you're in the lab. But when you're inserting a meter in the middle, again, the meter will have some resistance. If you're trying to measure the current that is flowing through that 1 kilo ohm resistor, and this would be the R internal. Let's write it right. R internal of the ammeter. And this is quite obvious here because the ammeter is in series. It's in the same pathway as our measured resistor. So ideally, we would want the resistance of that meter to be equal to 0. So we ideally would want to be 0. If it's even 10 ohms, which is a small resistance value, it's even 10 ohms is going to drop some voltage across it. And so the current is now reduced. So the actual current to the 1 kilo ohm resistance is not being measured. It's now lower. So ideally, the ammeters should behave like a short circuit. And a voltmeter should behave like an open circuit. Okay. Current through an open circuit is 0, and voltage across a short circuit is equal to 0. Short circuit means there are 2 points in a circuit. They are connected by a wire. So they are exactly the same point. If you try to measure voltage between the same point, there is no difference in electric potential, meaning there is no voltage between those 2 points. Hence, an ideal ammeter should not sustain any voltage across it. R should be equal to 0 ohms. So let's take a pause and let me know if you have any questions. Did that make sense? Let's give it a few more seconds. Any questions? Okay. All right, then let's get to our topic where we are trying to connect multiple loads to our sources, right? So the whole point of this is resistive circuit analysis, where we start with single loads and then we move to multiple loads. And multiple loads we can connect in a variety of ways. Two of the most common ones are series and parallel connections. Okay. A real life example of a series or parallel, a series connection would be your holiday lights, especially the old design filament light bulb of holiday lights. Those were all connected in series. So simply put, a series connection of components means a chain of components or a chain connection, and a parallel connection means side by side. Okay, that's like the best analogy of English words we can use. Now, this is something that would be covered in your physics classes. So have you studied in any other physics classes before? Not yet. Some of you might have. And everybody is taking 143 right now, correct? Okay. Can somebody send me a syllabus of that class? Yes. They don't teach the resistive analysis? Oh, I thought they were supposed to. Okay. Yes. It does get covered. Do you know approximately which week it was? Okay. Week 7 or something. Oh, okay. That's what you said. Week 7. Okay. So that's like near the end of the quarter. That doesn't help us. Yes. The same thing. Okay. All right. We'll learn it here, so it'll be better prepared when you get to physics then. Okay. So as I was saying, series connection. Real life holiday lights were one of the most common examples of a series connection. Parallel connections are all around you. Like every power outlet that you see here is all a parallel connection. Every single power outlet that we use in our homes, apartments, that you see at the workplace, they're all parallel. And you can see that like right along the back wall, underneath the lab benches, you see that long pipe running. A long pipe is just pulling out one connection at a time. So they're all connected in parallel. All these power strips, they're all in parallel. Okay. So let's talk about what it means. Series connection, as I said, is actually, you know what, before talking about that, let's talk about electrical node. An electrical node is simply a junction point in a circuit or a system where two or more components meet. Okay. So electrical node is simply a junction point. That is all, where two or more components are connected. So you could have two components connected like this. This junction point, actually, this entire wire is a node. It does not have to be marked with anything. Sometimes you may see a dot in a circuit, sometimes you may not. But anywhere you have two or more components connected, that is an electrical node. It's a junction point. Okay. Next, actually, let me draw one more illustration. Many times in circuits, you might see something like this. You might see something like this. Whether a dot is present or not, if a connection is implied, that means that is an electrical node. Now, an electrical node can be a very small dash, can be a short line, can be a very, very long line. In a schematic, it doesn't matter how we draw it out. Okay, everything is ideal, everything is theoretical. So a dot is the same as a small line, is the same as a very long line. Okay, it's the same electrical node. And any nodes connected by wires are the exact same node. Okay, so any nodes connected by wires are the exact same node. As long as you have an unbroken connection of wires or conductors, makes no difference. It could be 1 feet away or 1 foot away or 100 feet away, 1,000 feet away. Electrically speaking, it's the exact same node. The most common example I like to use again is power strips or your power extension cords. If you have a 50 feet, or let's say 100-foot long extension cord, you plug it into the wall, you would expect at the wall power outlet, you would have 120 volts, and 100 feet away, you would still expect to have 120 volts. Electrically speaking, it's the exact same node. Okay, so it's a 100-foot long wire, but electrically, it's the same junction point, no difference. So our power strips that you see all around here in the classroom, they are all same electrical node. That's why they can function. Now let's go to series. So series connection requires that there could be no more than 2 connections or 2 components at a single node. If there are 2 components connected to each other, that means there's a connecting node in the middle. And if there are no more than 2 components or 2 connections at that node, that means those 2 components are in series. Illustration was above. This is a series connection. You could have an unbroken chain of connections, and they would all be considered to be in series. The only criteria is at every connecting node, there should not be more than 2 components. It's like a chain. Okay. If a third component comes into the picture at any of the nodes, then they are no longer in series. That's a series connection. And so, the old design of holiday lights used to have these filament light bulbs, and you would add them all in series. So if one of the light bulb went out, was defective or faulted out, then the entire light would stop working. And that's because everything was connected in series. Current would pass through every single filament light bulb. All right, parallel. For parallel circuits or parallel components or parallel connections, you identify 2 nodes. Any component that is connected between those 2 nodes are said to be in parallel. Okay, so any component connected between 2 nodes are said to be in parallel. You could have two components connected between the same two nodes. You could have you could have 10 components, 100 components, 1,000 components, million components. But if it's the exact same two nodes, then they are all said to be in parallel. So let's say I have a node like this and I have another node like this. This is node A and node B. I could have an unbroken chain of all of these connected in parallel. Okay, they're all said to be in parallel. In a parallel connection, there are only two nodes. Okay, you just have two nodes. That's it. Doesn't matter how long that node is, but it's still the same electrical node. Let's take a pause. Let me know if you have any questions. Any questions? So the question being asked is which ones would be the nodes in the parallel circuit, right? In the parallel circuit. So in the parallel circuit, the nodes are marked as A and B. So this entire length of wire is one single node A, and the bottom, this entire wire is node B. As long as the wires are extended and connected, it's all the same node. So if I was to draw it out to be even more accurate, I would say this. Everywhere there's a wire connected to that place, that's the exact same node. So the entire structure is a node. A node evokes images of like a point or a dot, but electrical node is not that. In a physical system, electrical node can be a really long cable, can be a really long wire. Okay. All right. So let's now move forward with the concept of two or more loads connected to a single source. So we have the single voltage source and we have connected it to two resistors. Are the resistors connected in parallel or are they in series? What do you all think? One answer says parallel, right? Because it's the same two nodes. So we had two nodes at the top. Sorry, one node at the top, one node at the bottom. All three of them are connected in parallel. Now the property of, the quantity voltage is defined as the difference in electric potential between 2 points. So you have two nodes in a circuit. If you measure the voltage between those 2 points, you would obtain some value. If I measure the voltage here on the left, I get 12 volts. If I measure the voltage here in the middle, or if I measure the voltage here, what value should I expect? Volts. Absolutely. So parallel connection, the voltage is the same for all components. That's the big property that you have to understand and recall. Okay. Now, in the statement, you might read in books or you might hear somebody say in a parallel circuit, voltage remains the same. Well, it doesn't mean remains the same in the sense that the voltage is a constant value for all components. So when you say same, it means it's the same for all components. And here's the principle behind it. The voltage that appears across a parallel connection is a result of all of those components working together or acting together. So it's a cumulative effect. Okay. And that's why the voltage is the same for all components. If one of those components changes value, then the voltage could potentially change. In this case, we have a voltage source connected between those two nodes. If there is a source, the property of a source is to supply its rated voltage. So the cumulative effect of all three working together is that the voltage source is supplying 12 volts. That means there's 12 volts across the voltage source, there's 12 volts across the middle resistor, there's 12 volts across the resistor on the right. So you got 12 volts across both resistors. To analyze this, all you have to do is apply Ohm's law, V equals IR. If you apply Ohm's law, you have the voltage 12 volts, the resistance 1.44. You can find the current, 8.3 amps. And once you have the current, you can calculate the power. Okay. So total current is 8.3 plus 8.3 gives us 16.6. In a supply, current always moves from minus to plus. Fundamental concept. In a power supply, current is always shown as going from minus to plus, meaning a lower potential to a higher potential because it's a source, it is supplying energy. Okay. For every other component, for everything else, current always behaves like any other quantity. It always goes from high to low, always goes from plus to minus. Yeah. So question being asked is if we supply negative voltage, does it go the other way? So negative voltage meaning, did you just flip the sign of the voltage or did you create a dual power supply? So there's negative and then there's flipping a voltage source is different than actually sending a negative potential. Even negative is nothing. So let me explain. So let's finish this first and then I will talk about that. So here, voltage seen by each load is 12 volts. Apply Ohm's law, you get current 8.3 amps going through both. If it's 8.3 amps, that means that total current coming from the source would be 16.6. You can calculate power for the source. Power for the source would be, let's say PS is Vs times Is. So it's 12 times 16.6. And then each individual resistor would be 8.3. We can calculate 12 times 8.3. And so okay, so approximately 100 watts each. So if you connect them in parallel, they're each consuming 100 watts. So the implication here is if you connect two loads in parallel side by side, they're going to share the same voltage. If they share the same voltage, that means the demand from the supply is now doubled. If it's a single resistor, it's simply 12 volts applied to a single resistor, still 8.3 amps, still 100 watts. And you added another connection in parallel. So now the power requirement from the source is doubled because the power requirement is doubled. So now instead of 100, it needs to send out 200 watts. And you can easily do this experiment at home if you want. You buy 2 space heaters, each 1500 watts, plug it into the same power outlet or a power outlet like in the same room next to each other, run both at full blast, and within a few minutes, your circuit breaker should trip. Is because when you plug in 2 space heaters in the same circuit, now you're double the load requirement. Now, each heater, and I believe I've talked about this before, all heaters in the market are the same, rated for 1500 watts, because the maximum current coming from a power outlet is 12.5 amps. So a single circuit can only supply a max of 1500 watts. So no matter which heater you buy, it's still going to run at 120 volts, still going to pull 12.5 amps. So if 2 heaters are running from the same power outlet or right next to each other, they're both trying to pull a lot of power, a lot of current, which that residential circuit cannot supply. And so the circuit trips. You have to go outside and flip it back. Okay. If you're in a residence where you have access to 2 heaters, you can try it out safely. Just don't do it at night. Okay. So final 2 points. The total value of the current drawn from the source, of course, we had 16.6. And then what resistance does the source see? Well, the resistance that is seen by the source from the perspective of the source is that it is half. It is 1.44 divided by 2, because now you have connected 2 in parallel. And because it's halved, now it's sending more current. Okay. If you had connected 3 resistors, it would be R divided by 3. 4 will be R divided by 4. Okay. All right, let's take a pause. Let me know if you have any questions, and then I'll go back to the question that was asked earlier. Did all of that make sense? Hopefully. Okay, remind me of that question. Oh, negative and positive power supply. Okay, all right, let's, I've talked about voltage sources and current sources, right? Voltage source and a current source, this exact same thing. You just run it in CV or CC mode and becomes a voltage source or a current source. Now, and also did that one-dimensional diagram about voltage? Not yet. I did. Somebody saying yes, somebody saying no. I think I did. Let me see. I have to quickly scan through. When was this? This one. That one-dimensional diagram, A, B, C, D, E, F, multiple points in the circuit. You're trying to measure the voltage from a single reference point, right? So the question being asked was about negative voltage or negative power supply. One thing I'd like to point out is that these quantities, voltage, current, power, energy, these quantities are never positive nor negative. Okay, they just are. It is only us humans that when we're trying to analyze a system, we like to draw out a schematic. We call that schematic a circuit diagram. And then everything is based on the law of conservation of energy, meaning energy is neither created nor destroyed. It is simply transformed from one form to another. So if you have a closed system where you have a source, you have multiple loads like resistors, then the source is supplying some energy, which would be in the form of voltage or current, meaning it's supplying some power. That energy is consumed within the circuit and the system. The output could be mechanical, could be optical, could be thermal, depends on the system, obviously, but it's converted, and a lot of it also could be released as heat. That is the byproduct. Now, when we write equations to describe the system, we would have the source supplying some energy. So we put a minus sign onto everything regarding the source. So voltage for the source, we put a minus sign. Current, we put a minus sign. Energy, we put a minus sign. And everything that is receiving the energy, like a resistor, for instance, we put a plus sign because it's receiving energy, it's receiving power. So in terms of voltage and in terms of current flow, this is what it would look like. So we had, let's see, where were we? We already did this right here. So in this system, not in this one, sorry, this one. In the system, remember I said that current always flows from high to low. So if you have a resistor in a circuit, and we don't know the direction of the current in this resistor, we look to see if there's a polarity of the voltage. If there is a polarity, which is plus and minus, then current always flows from plus to minus, meaning it goes in this direction. Current is like any other quantity. If you take fluid like water, because of gravity, it goes from high to low. If you take temperature, it always goes from higher temperature to lower temperature. Pressure, again, high pressure to a lower pressure. So current always also flows from high to low. In this case, high is indicating the higher electric potential to the lower electric potential. Okay, so for a resistor, we indicate the current flow as going from the higher polarity of the voltage to the lower polarity. The flip side is, if current direction is given to you, then the point of entry into the resistor is where you should note it as plus, and the point of exit would be minus. Okay, I'm getting to your point. It's a long-winded, but these are all fundamental concepts. So I'm glad you asked that question. Again, this is very important. Okay, current flows from high to low, so it always goes from plus to minus. If you're given the current direction, you can note the polarity by the point of entry. So point of entry is plus, point of exit is minus. So you should be able to figure that out. Okay. Now, when we are faced with a circuit like the one we just have right here, we have a voltage source given to us. And we have these two resistors given to us. We have no other indication of the current direction or the voltage across any of the other components. For a source, it is the opposite. We mark it with a minus sign. So for a source, the current moves from minus to plus. And only for a source, and only because we want to represent it as supplying energy. So we put a minus sign. So when we apply KVL, when we apply KCL, this voltage would mathematically be represented with a minus sign. Otherwise, our equations would never balance out to zero. Okay. Again, law of conservation of energy. All the energy supplied must be equal to the energy that is consumed or received. Okay. So we have a voltage source. In a voltage source or a current source, current always goes from minus to plus. And so it's going in the opposite direction, opposite of the resistor. Then it has no place else to go except in this direction. This is all the same node, by the way. Which is what we just pointed out above, right? Same node. So current comes through here. When current comes through here, it's going to split. Some of it's going down the middle resistor, some of it's going down the far resistor. And then because the point of entry is from the top, voltage will be plus at the top and minus at the bottom. Okay. That's how you would note the current direction and assign polarity to the voltages to the resistors. Okay. Did that make sense? Right. Now, the question that was asked earlier, what happens if we flip this? Any guesses what happens if we flip it? So we flip this. Sign reverses. Absolutely. Because flipping the source or terminals is not changing the value of the resistances. The value of the resistor is still 1.44. Does not really matter where it's going from, right? Flipping or switching out the terminals of the source does not make any difference. The only thing is current is now going in this direction. And so it's going up. And then the plus sign would be at the bottom. That's all it is. Okay. 3 minutes. Yeah, go ahead. Absolutely. You can apply. So a question being asked is about applying KVL to these circuits. Doesn't matter which circuit you apply KVL to, and doesn't matter in general, it doesn't matter how we sum up KVL or the voltages. You could sum up in the clockwise direction. You could sum it up in the counterclockwise direction. You could assign positive and negative to the sources in one direction and negative and positive in the other direction. You would still end up with the exact same equation. So yeah, no, it wouldn't make any difference. That's the answer. Okay. So switching a source or flipping the terminals would make no difference. It would work exactly the same it is. Now, the reason I brought up that one-dimensional chart was because in that example I had shown, depending on what a reference point is, some voltages could be negative. Remember, we had A, B, C, D, and then E was below A. And if A was a reference, then E would be negative. Or if D was a reference, then all other voltage would be negative. But the voltage between the points would not change. That remained fixed. So dual supplies, which I don't know if 145 you will work with dual supplies or not. But what a dual supply is you have two power supplies, and all you're doing with those two power supplies, let's take the example of a battery. You can create a dual power supply with two batteries. Okay. If you take two batteries, and of course, this end is plus and this is minus, and let's say each one of them is worth 3 volts. Okay. Standard standard batteries are like 1.5 volts, but let's just take 3 volts. All we need to do to create a dual power supply is basically connect the negative end of one battery to the positive end of the other one. And all we are doing in that case is, and let's draw that one-dimensional diagram again. Voltage V on the y-axis. And let me note down A, B, C, and D. Voltage A was at 3 volts. B was at 0. as far as that battery was concerned, right? But now, because I stuck the other battery below it, this is C and this is D. Now C is plus 3 volts as compared to D. But if C is connected to B and I use this as my reference, then what is VD? Come on, you already know this. -3. And that's all a dual power supply is. That's all it is. Then you're applying a true negative voltage, all because we are using that midpoint of the power supply as our reference. So all lab benches, when you get to 145, you take a look at the power supply. All benchtop supplies will have 3 channels, 3 independent power supplies. 2 of them can go up to like 30 volts. 1 of them can go up to 6 volts. The 2 30-volt supplies, they are provided because we can create a dual power supply using those. We connect the negative and positive of the two supplies together, and that connection in the middle, that becomes a reference point for the entire circuit. It does not have to be connected to ground. You can just call it ground without connecting to ground. Okay. All right. Bell has rung, and we have gone over a minute and a half. So we'll end class here today. Quiz on Monday, based on the material we have covered this week.